Mostly, I kind of wanted your opinions on whether you liked having, um, yeah, so I guess I wanted to know, and you can think about this before you answer, when I send you the form, which I'll put together tonight, um, whether you like having the class fully synchronous or not. The reason I have the class fully synchronous, meaning that like I expect you to be on here at the same time as me teaching you, basically just like we're in a real class, except I'm at home and you're at home. The reason I have it set up that way is because personally, I feel like that's the way you're going to be most successful, because it kind of forces you to have to be on at a certain time. However, since I only usually have one person who even has their camera on, maybe two, if I'm really lucky, three, I don't even know who's on here, who's actually listening, who's paying attention. And sometimes I wonder if it might be best if I were to record a lecture and then maybe have the lecture that I record be, I don't know, like an hour, because the thing is I could get through things a little bit faster if I wasn't constantly stopping to be like, do you guys have questions? Does anyone have questions? And then having like, I don't know, an hour of class time where it's basically kind of like a discussion section where you would come and we'd go over problems and you would kind of ask questions. We don't have to do that, but that's kind of what I'm interested to know. Like, would you find that to be more helpful? And so I'm going to send out a form just kind of with questions like that. And then so that, I mean, I kind of have answered Sebastian's question of why change the format. But I also feel like a lot of you aren't doing that well. And maybe this way of doing it isn't necessarily the best way. So, yeah. Yeah, and like Karen was saying, at least if it's on a recording, I mean, you would have to make yourself watch it. But the nice thing is that you could pause it and be like, wait, hold on, I don't get this. Whereas after class, if you've seen it live, you might not go back and watch it again later, or you might not go over it again. Because I really want, I feel like I want to spend more time interacting with you and answering questions, whereas during class, there's not a whole ton of time for that. And then I feel like if you do have questions, you don't ask. So I really want to see if there's a way that we can incorporate more of that. The thing is, I can't get through the material and do that at the same time. I just thought we would try it and see, and maybe even switch from Google Meet to Zoom so that we would have a little bit more capabilities for, no, Mia doesn't like Zoom. Oh, see, this is why you need to have your camera on, because see, I see that she's shaking her head. She doesn't like that. Most people I know are just like, Google Meet, you use Google Meet, like you're so, I don't know, behind the times. I don't know. I don't know, but I just want to get your thoughts and see if you have any opinions on it. Why is Zoom better? I don't know. It just seems like a lot of people have negative reactions about Google Meet. I don't know. Zoom is the worst. Oh, well, see, this is why I need to send out a survey, because I don't know. Maybe, oh, see, Zoom is not good. Okay. Google Meet's better than Zoom. See, it lags. Okay. See, this is exactly why we need to have a conversation about this sort of thing. Like, I need to hear this from you. So I'm going to send out one of those Google form things, and then you give me your thoughts. I'll have some specific questions on there, and then I'll say, like, you know, did you have something you wanted to add? And then you could give me some thoughts on if you had ideas for things that could maybe help you to become more successful in the class. So I don't know. I want us to really be learning, and I want to make sure that that learning is happening. And I'm kind of concerned that it isn't to the extent to which I would like. Google Meet is a lot more convenient since I don't, yeah. Yeah, I mean, that's honestly the reason I set up Google Meet to begin with, is because last spring we all went online and I was just like, ugh, not sure what to do. And then I just picked Google Meet because it seemed like it was in everybody's Google Suite already. And all they had to do was just go to the calendar and click and they were in. And it was just one less thing to worry about. Well, and at the time, ECC didn't have a Zoom license. We do now. So I don't know. All right. So I would like your feedback on that. So when you get it, because it seems like we have thoughts here. Some people have thoughts. So when you get it, answer it. Don't just leave it. Don't just be like, whatever. Other people will respond because I want to hear what everybody has to say. The ones who vote make the decisions. And that is true for every walk of life. I need to hear from you. If I don't hear from you, then I don't know. So I'm going to do that. Yes, democracy. Power, the power. You won't have the power, so you got to respond. There's something I was going to add to that. I can't remember what it was, but I don't know. Yes, don't forget to vote this election. Yeah, I was going to remind you of that too. Oh, Mia can't vote. Are you too young, Mia? She's too young. Yeah, don't worry. We'll vote. Okay. There's also a debate Thursday, which will doubtless be very entertaining. So you should watch that too. I mean, it's not like you're going to change your mind at this point, but it's nice to be informed, see what's going on, catch all the highlights at least, know what everyone's talking about the next day when they're talking about flies and all such, and you're like, huh, what are they talking about? Okay, let's talk about math. We are in 4.2. I just said let's talk about math, but I forgot that I have one more thing to mention. It's midterm. Our midterm date is officially today. I entered your midterm grades yesterday just because we won't have another test before your midterm. So at this point, any homework assignments that you turn in aren't really going to change your grade enough to even change the letter. So I just uploaded your midterm grade as whatever grade it is currently. I don't drop your lowest test score and your lowest quiz score and your lowest 3 homeworks until the end, right before the final. So the class before the final, you'll be able to see your grade with all that stuff dropped. Partly that's to motivate you because I want you to feel the pressure to do better if you need to do better. Some of you are doing just fine, so you don't need to worry about it. But yeah, so it's midterm. Your drop date is, I believe, I'm going to remind you of it again because it is quickly approaching. Here we are, mid-October. Your drop date is so close. 11/8, November 8th, and that's a Sunday. So I'm going to remind you as that date draws nearer. Just in case you wanted to take the W, you have to do it by 11/8. If you don't want to take the W, fine. Doesn't matter to me. Just want you to know so that you don't say, well, I didn't know. I had planned to take the W and now I've missed it. Don't want that to happen. Okay. I don't think there's any more housekeeping. Okay. Wonderful. Okay. So last time we were talking about evaluating logarithmic expressions, and I gave you some log expressions to evaluate on your quiz that you took today on D2L. I hope that multiple choice wasn't confusing, or not the multiple choice, it was a matching. You were supposed to match it up with the number on the right-hand side. So hopefully that wasn't too confusing. All right, so we talked about that. Now let's talk about graphing logarithmic functions. Characteristics of logarithmic functions. And this is for log base b of x. The domain of f of x equals log base b of x consists of all positive real numbers. So we're looking at a domain from 0 to infinity, not including 0. The range of f of x equals log base b of x consists of all real numbers from negative infinity to positive infinity. Excuse me, I have to go yell at some children. Hold on. Guys, go downstairs. Sorry about that. Okay. The graphs of all log functions of the form f of x equals log base b of x pass through the points 1, 0, the point 1, 0, because f of 1 is log base b of 1 equals 0. The x-intercept is 1. There's no y-intercept. Now, that might sound familiar to you because you might be thinking, wait a second, wasn't that the case for the exponential graph? Opposite. The exponential graph, we said, had that anchoring key point at 0, 1, not 1, 0. So we're going to talk about the connection between an exponential graph and a logarithmic graph. All right, so there's no y-intercept with a log function. There's no x-intercept with an exponential function. Number 3, if b is greater than 1, f of x equals log base b of x has a graph that goes up and to the right and is an increasing function. If b is between 0 and 1, the log function has a graph that goes down and to the right and is a decreasing function. F of x equals log base b of x approaches but does not touch the y-axis. The y-axis is a vertical asymptote. So similar to how with an exponential function, the x-axis is an asymptote. What page are we on? We are in 4.2, page 2, Elizabeth, or Beth. I always call you Elizabeth because that's how your name shows up. I don't know if there's a way to fix that. Okay. So what we're going to do is graph the functions in the same rectangular coordinate system and show a table of coordinates for both functions. We're going to go through this, and then we're going to talk about the connection between the two. So f of x equals 3 to the x and then g of x equals log base 3 of x. So we'll look at some particular values of x and try to make some connections here. Now, normally when we're graphing an exponential function, we include values that start maybe at like x equals -2, depending on the situation. You can do that here, but you're going to find that you're going to run into a problem because the domain of a log function is positive real numbers. That means I cannot include values of x for a log function that are not positive. But we can go ahead and put these values down for our exponential function, and then we'll get some different values here for our log base 3 of x function. And then talk about why we might need different values. All right, so 3 to the -2nd power is 1/9. And I believe we graphed 3 to the x last week, or at least we graphed 1/3 to the x. When x equals -1, f of x is 1/3. And we have that anchoring point at 0, 1. 3 to the 1st is 3. 3 squared is 9. So you can go ahead and start to plot these points to create this function f of x. So we're at -2 and then about 1/9. So really, really small here. It just kind of looks like it's almost sitting on your x-axis. It's going to be very close. -1 and about 1/3. 0, 1. 1, 3. And then 2, 9. So 9 is going to be a little bit too high. 7, 8, 9. I don't know, something like that. So there's your function f of x. Now, you'll find that you can graph g for some of these values, but only for the positive ones. So for instance, when x is equal to 0, well, we can't do that because then we'd be looking for log base 3 of 0. That means 3 to what power would give you 0? And you'd be stuck. We're not defined there, back to your definition for the domain, so we can't include it. So we can start at a value like 1, and we can look for a log base 3 of 1. What this means is 3 to what power equals 1, And if you're not sure, any real number to the 0 power would give you 1. Gosh, let's see how small I can possibly write in here. So it'd be 3 to the 0 power. So your y value would be 0. Let's put this into an ordered pair. X was 1, y was 0. And remember, we said up here that that point is always going to be on the graph of your log function. Let's see. Your graph is always going to go through the point 1, 0. And that's why. So we'll go ahead and include that point. Now, we can also talk about what happens at 2. So log base 3 of 2. You'd be asking yourself, well, 3 to what power gives you 2? Does anybody know what the power would have to be? 3 to what power equals 2? Off the top of your head, without using a calculator, because I know some of you have taken college algebra at some point in your lives. Can we do this without a calculator? 3 to some power gives us 2. I would say no. This is something you need a calculator to do. So this is why we need to think a little bit more logically about the values of x that we choose here for this function. But let's say we decided to go with 3. Log base 3 of 3, now that we could do. What this means, sorry, I should be using arrows here, is 3 to some power equals 3, and that power would have to be 1. So that would be your value for g of x in that case. So when x is 3, g of x is 1. Now, it's going to be kind of hard to see here. I'm going to include one more value. Now, looking at what we've done so far, we have 3 to some power equals 1, and that power was 0. And then we have 3 to the first equals 3. What we're trying to go for here is 3 to the second equals 9. And the log equivalent for that would be log base 9. So log base 3 of 9, which would be 2. So we could go ahead and also use the point 0.92. Now, again, our graph doesn't quite go out that far, but we can sort of work our way out here. 7, 8, 9, 2. Now you can start to see what's happening here at these points. If you're thinking about your coordinates, you had a point on f of x, 2, 9. You had a point 1, 3. But on g of x, you have a point 3, 1 and 9, 2. Your coordinates are flipped. So if you're not sure what value of x you should look at next, I'd maybe go with one of these values that you already know something about. Maybe instead of using an exponent of 1 or 2, maybe think about your exponent as being some sort of negative value. So you could go down. I'm kind of running out of space here. Let's see. Yikes, I really ran out of room. Let's see, where should I put this? Let's see, g of x equals log base 3 of x. Oh, that's page 2. I was like, wait a second, I didn't write an exponent there. Okay. Let's try letting x be some sort of fraction, like maybe 1/3. So instead of letting y be a third, we'll let x be a third. So this will be log base 3 of 1/3. Well, essentially, you're trying to ask yourself 3 to what power equals 1/3. Well, you already know that because you did that problem right here already. And you know that power is -1. So you know that when x is 1/3, y is -1. Now you can really start to see what's happening with these points. Notice that in each case, each time we graphed an ordered pair for g of x, we had the inverted ordered pair already written down for f of x. What this means is that our functions f and g are inverse functions. And we can go ahead and say that that would happen for all of their points. So for instance, f of x has a point at -2, 1/9. That means g of x has a point at 1/9, -2. Notice that your function g is supposed to have a vertical asymptote at x equals 0, the y-axis, and it does have that. So we can go ahead and say that our graph is just going to kind of head that direction back down as it approaches the y-axis, and it's going to increase as x gets larger. Remember, we talked about inverse functions in 2.6. We said that we know that two functions are inverses if, well, really we talked about their coordinates being inverted, but we also said that their graphs would be reflective about the line y equals x. So let's go ahead and conclude here that f and g are inverse functions. Their graphs reflect over y equals x. And their coordinates are opposite. We'll say they're opposite. Or inverted. Now, I think we can all agree that it was much easier to graph the exponential function f of x and not so easy to graph the log function. But that's okay, because now you know that in order to graph a log function, you just need to be able to graph its corresponding exponential function. So that's what you're going to be doing when you graph log functions. I'm never just going to say graph this log function and just plug in a bunch of points into the log function. I'm pretty much always going to tell you in the direction, use the graph of the exponential function to graph this log function. So you'll graph the exponential function first, and usually you'll graph that with some sort of a dotted curve. And then you can invert the coordinates and reflect it over the line y equals x to get the graph of your log function. Does anyone have a question on this example or on this concept? So you kind of see how the graph is behaving, what you're expecting it to do. We got to follow these asymptotes and then just invert those coordinates to get from one graph to the next. All right, now you're using transformations. The graph of a log function is given. Select the function of the graph from the options. All right, you figure out which one you think this is while I finish up my attendance. All right, what do we think? A, B, C, or D? I have a B. Anyone else? What do we think? Nobody else wants to chat a guess? All right, we have a guess of A. All right, so I see B, A, B. 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 Oh, lots of B's. Interesting. There's another A. All right, the A's have it. B would be correct if it had parentheses. So B is the graph shifted down 2 units. A is the graph shifted right 2 units. Now, if you'll remember, your log function has a vertical asymptote on the y-axis. So that's really what you're thinking about here as you consider what function this is. Because you end up seeing this behavior where it appears that your particular graph has a vertical asymptote at right about x equals 2, that should be the signal that it looks like it's being shifted to the right. If I think maybe we were thinking a shift up or down just because maybe we were thinking about having a horizontal asymptote, but remember that log functions don't have horizontal asymptotes, they have vertical asymptotes. So definitely A shifted to the right 2 units. So if you think about having this vertical asymptote here at 2, you can see that your graph has been shifted to the right 2 units. Oh, thank you for playing, everybody. You can also pop this into your calculator and verify if you want to do that. Oh, wait, we don't know how to put log functions into our calculators. That's okay. You will know probably by the end of today, as long as I get to it. We will talk about how to do that. Your calculator might have a log template. Not everybody's does, though, so I will not use it. But when we get to that, if I find it, I will tell you how to look for it. Okay. All right, the domain of a log function. Now, skip number 13. We're not going to worry about what happens when we square that value. But we will talk about just regular old cases like number 12. Remember we said that the domain of the log function had to be positive values. However, we must also consider the case that something is happening inside the argument of your log function. We talked about the domain of the log function for log base b of x. And we said that if we had log base b of x, then the domain was positive numbers. Notice we don't always have just x. Sometimes we'll have x plus some value, x minus some value. You might have 2x. Any number of things could occur here. And it's really important to be able to find the domain, because when we solve equations next time around, you need to be able to tell which solutions will actually work for your log expression and which ones will not work. So to find the domain, we need to verify that whatever is in this log argument is positive. So you're going to take your log argument and just force it to be greater than 0. I can't take the log of a negative number. And then you'll just solve this inequality. And then you'll write this in interval notation. So we know we're looking for values of x that are greater than -6. Because we don't have greater than or equal to, I can't include a bracket. I have to keep an open parenthesis. And you can even kind of eyeball this and make sure, like for instance, if x is -5, well, -5 plus 6 is a positive number, so we're good there. If x is 0, 0 plus 6 is still positive. The only way this expression is going to go negative is if you choose a value that's below -6. And it'll be 0 if your expression is -6. And we can't have 0. It's not in the domain of our log expression. Questions on finding the domain? Okay. We won't need to look at these equations, which is why I'm not having you look at the domain for those. Okay. Common logs. So, you know, I could have sworn I mentioned common logs last time. They were on the first page also. Yeah. This looks like the same chart from page 1. It was so long ago. Yeah, so we already talked about this. General properties and common logs. So same exact chart as we talked about last week on Wednesday. We talked about the fact that a common log is a base 10 log. So a base 10 is implied. That means that log base 1 is the same thing as saying, or I'm sorry, log of 1 is the same as saying log base 10 of 1. Now, if you want to write the base of 10, that's fine. If you're entering logs in MyMathLab and you have a log base 10, you should be able to write it as log base 10. Sometimes students forget to just not include the log because you get so used to writing the base of the log. If you forget to not write it, it should be acceptable. MyMathLab should accept either one of these when your base is 10. But that's because 10 to the 0 power equals 1. So we have these same rules that apply. You can kind of see these rules a little bit more clearly if you include the base. That's why I tend to write it. I just feel like it looks more obvious when you put the base on there. Otherwise, you're sitting there and you're like, wait a second. I don't know. What is base 10? Like, what is this log doing? I think it's just easier if you put the base in. So log base 10 of 10 means 10 to what power equals 10, which is where you get that 1. Same idea here. You have log base 10 of 10 to the x. If the bases match, then you just keep the exponent. And then same here. 10 to the log base 10 of x. If the bases match, you just keep that log argument. So it's the exact same rules you see over here on the left, just for the special case that your base is 10. All right. So let's use these log rules or log properties to simplify logs without a calculator. The worst part about giving you guys tests remotely for something like this is that really this should be done without a calculator. And normally on your test in class, if you were in class, I would give you a no calculator part of the test that you would have to go through this and do it without your calculator. It's a little bit harder to do that when we're at home. So there won't be quite as many of these in that case. I'll have to try to get more creative with them. All right, if you need to write the base, write the base. The goal is to do this without using your calculator. Of course, anybody can pop this into a calculator. The goal is to know what this is without having to use your calculator. So what this is really saying is 10 to what power equals 1,000. Remember, you need to be very comfortable moving back and forth between logarithmic notation and exponential notation. So we should be able to take this logarithm and turn it into exponential notation very easily. The exponent that we're looking for in this case is 3. 10 to the third is 1,000. Therefore, log of 1,000 is equal to 3. Now, you are probably going to do enough of these that you start to feel really comfortable with them, and you won't have to go through and rewrite them using the log base 10 notation and write them in exponential form. But that's up to you. I'm going to write them just because I feel like it's a little more instructive, especially for people who aren't as, or don't feel that same level of comfort with those. All right, number 15. Again, we're using the properties here. You can go back and look at them if you want to do so. We just talked about it, though. This is 10 to the log base 10 of 7. Remember that if the bases match, which they do in this case, the answer is just the log argument, which is 7. And you can always rewrite that back to log form, and you'll see why. But that is from property, I think it's number 4. Yes. Property number 4. And then for number 16, we're taking 9 times log base 10 of 10 to the 6.2. Now, before today, if I would have said, here, evaluate this without using a calculator, you would have thought I was nuts. But you can kind of see now how you can use these rules or these properties for logarithms and pull this apart into something that's much easier than what it looks like. Your bases match, keep the exponent. The only thing you have to remember in this case is this constant multiple of 9 is in front of the logarithm. So you have 2 different expressions going on. The 9 has to stay as a constant multiple, and then for the log expression, your bases match. Keep the exponent. And now your answer is just 9 times 6.2, which is 55.8. So you will also see some like that where you have a little bit more of an expression going on versus just straight up using a property. Does anyone have a question about how to use the properties for simplifying logarithms without using a calculator? All right. What if the base didn't match? Well, Benjamin, that's a good question. If the base didn't match, then you would not be seeing it in this section. Yeah, if the base didn't match, you'd have to use your calculator in order to evaluate this. And I'll show you how to use your calculator to evaluate log expressions later. Your calculator automatically does base 10 expressions for you. So this one you could just pop into your calculator. But as far as any other base other than 10 or E, which we'll talk about in a minute, you would have to do that in your calculator. So the ones that you're seeing in this section are only ones that you can do without a calculator. Use the formula R equals log of A over T plus B to find the intensity R on the Richter scale, given that amplitude A is 444 micrometers, time T between waves is 3 seconds, and B is 3. Round your answer to 1 decimal place. So we're just going to substitute these values into the expression and then simplify to find the value of R. So let's see. We're looking for R. We're going to take log. If you want to write the 10, write it. You don't have to. I'm just going to write it. Log base 10 of A over T. So we were given the value of A as 444. And then T, the time T between waves is 3 seconds. And B is 3. Richter scale is earthquakes, yes. I don't know why this thing is not beeping at me anymore. They changed my Google Meet and now, I don't know, it doesn't beep. My sound is on, but I'm not getting a beep. So sorry, I don't know when people are talking in the chat unless I keep looking at it. Okay. So log base 10 of 444 divided by 3. I'm guessing that this is going to end up being a calculator problem, which is not a bad thing. If you take 444 and divide it by 3, you get log of 148 plus 3. So let's go ahead and use our calculator to simplify this expression. Maybe. When you are entering a log in your calculator, log base 10, you have a log button on your calculator that will do that for you. This assumes that you're using base 10. If you have a log other than base 10, then this log function will not work for you. But you can hit that log button and it will pop up with log. You can enter 148 or you can enter 444 divided by 3. Close off your parenthesis. Don't forget to close it off. And then add 3 and see what you get. Pretty much any calculator will do this for you, by the way. You can even use your iPhone calculator to do this. It is a pretty standard operation. I'm going to go ahead and use 2 decimal places here and go with 5.17. Does anyone have a question about how to enter this this base 10 log into your graphing calculator or to your calculator? Okay. Wonderful. All right, the other type of log, the special type of log we're going to talk about is a natural logarithm. The natural logarithm is a base E logarithm. So again, we're using these same properties that we've talked about already twice now. The difference is that in this way that we write a log, we write it as ln. And people always want to know, if it's natural log, why do you write it ln instead of nl? I don't know. I'm sure you could Google that and find out very quickly. I never have, because I always just took this as the way it is. But that's the way it is. ln means natural logarithm. So an ln equals a log base E. Now, for some reason, I find that students have a harder time evaluating these natural logarithms, and I think it's because they don't switch over. So you don't have to use the notation of log base E. I just always find that it's a little bit more intuitive to use that, because then you can use the rules the same way that you've always used them. If you start to feel really comfortable with them and you just know that the natural log is a log base E, more power to you, that's fine. But we use a shorthand notation ln to represent a log base E. So you can see here, log base E of 1 equals 0. That's because E to the 0 equals 1. Log base E of E equals 1. Well, that's because E to the first equals E. And so on and so forth. Log base E of E to the x equals x. As long as your bases match, keep the exponent. And then E to the log base E of x equals x. Again, your bases match, you're going to keep your log argument. So you have these same properties that you're seeing, this time using E instead of just some real numbered base or a base of 10. And again, you're going to be asked to evaluate expressions without using your calculator. So natural log of 1, you're going to get really good at doing this. You're going to use this one all the time, and you're going to see it all the time in calculus. But right now, you're just like, wait a second, ln1? I don't know. If you're not sure, change it to log base E. And then you're asking yourself, E to what power is 1? Oh, well, it must be 0, because any number, any real number to the 0 power equals 1. And also you have that in your properties up here. The natural log of e squared is really just the log base e of e squared. As long as your bases match, you keep the exponent. I find these so fun. I really love logarithms. I really do. All right, the natural log of e, this is another one that you're going to see all the time. The natural log of e is just log base e of e. And if you're like, okay, how does this help? Well, e is just e to the first power. As long as the bases match, keep the exponent, you get 1. And of course, you have these written here also. So if you want to highlight these boxes wherever you see them on your notes, so that you can find them more quickly when you're going through your homework or working on your exam, that's fine. You're going to be using these quite a bit as we work through solving equations too. Are there questions on 18 through 20? Okay, all right. Evaluate or simplify the expression without using a calculator. Now, we have not seen any of these radical expressions today, but we did look at a couple of them on Wednesday. And we said that anytime you're given a radical expression inside a logarithm, you need to change it to use a rational exponent. So I'm going to start out by changing my natural log to log base e. Again, you don't have to. I just find it's easier to look at. And then instead of saying the 6th root of e, I'm going to change this to e to the 1/6 power. In the same way that a square root is a 1/2 power and a cube root is a 1/3 power, a 6th root is a 1/6 power. And now you can see from your properties, you've got the same base, you'll keep the exponent. So nothing too crazy there. I keep thinking there's one more page to this, but there is not. All right, we're going to move on to 4.3. So I will give you a moment to gather your notes. .3 properties of logarithms. Now, all of the stuff that we're doing here in 4.2 and 4.3 and also 4.1 is we're really working our way up to what we're going to be doing on Wednesday, which is solving logarithmic and exponential equations. So we're going to be doing a lot of work trying to determine not only how to evaluate logarithmic and exponential expressions, but we're also going to talk about how to rewrite them so that we can get a desired quantity so that we know how to work with these values in order to solve an equation. A lot of times when we're solving a log equation, we're going to have to rewrite the log in a way that gets us into a proper form. And we're really going to be focusing on that right now in 4.3. We're going to talk about different ways that we can rewrite logarithmic expressions to kind of help our cause a little bit. It is really important that you are feeling very comfortable with this before we're solving equations on Wednesday. So I hope that you will have a chance to get to your homework between tonight and Wednesday. I hope. Don't know, but I hope. We're going to use a product rule, a quotient rule, a power rule. We're going to expand, we're going to condense, and then we're going to talk about the change of base property. And that's what a lot of you are looking for because it's going to help you to evaluate logarithms in your calculator when you have a base that isn't 10 or isn't e. So we'll talk about that at the end. Okay, So the first rule that we're going to talk about is the product rule. Let b, m, and n be positive real numbers such that b is not equal to 1. Log base b of m times n can be rewritten as log base b of m plus log base b of n. Now, I want to make very clear, because one of the most common mistakes I see with the product rule is students always want to say that log base b of m plus log base b of n must be equal to log base b of m plus n. No. It's a product rule. It's not a sum rule. It only works for products. And I know that a lot of we get very used to using the distributive property, and we see addition and we use addition. We don't usually go from multiplication to addition, but for this logarithm rule, we do. So make sure that you understand that the sum of these two logs does not equal the log of the sum. It doesn't work that way. The log of a product equals the sum of the logs. So that's important. Okay, so that's the product rule. The quotient rule. Again, we're letting b, m, and n be positive real numbers such that b is not equal to 1. Log base b of m divided by n is log base b of m minus log base b of n. So again, we're not saying, I don't know, what have I seen people do? They do this. They say, oh, it must be the case that log base b of m over n is log base b of m over n. Not the case. So don't do these things. Make sure there's a big no there. Okay, so these are not equivalent. You can't do that. You know, in the same way, you can't take two logs and multiply them together and get the log of the product. It doesn't work that way. These are your properties. You cannot just create whatever you want willy-nilly because you think it works. These are the properties you have to follow. This is what you have to work with. Now the power rule, I saw a big note on my notes saying, change this or fix this. This p should be an exponent, but it looks, when I convert from like one type of document to the next, when I converted these to PDF for some reason, the font changed a little bit. So I'm just going to rewrite this so it's really clear. Log base b of m to the p is equivalent to b times log base b of m. It's not m times p, it's m to the p power. Now this one, this power rule, you're going to use a lot. I mean, you'll use all of these a lot, but I feel like the power rule you use the most often. And again, this is all stuff that you're going to have to learn to work with as you move into calculus. So you're going to be using these rules all the time. They're not going anywhere. It's not like, oh, I just need to see them now, get this test over with, done. No, these are going to be around throughout your math lives after this. So get used to them. The logarithm of a number with an exponent is the product of the exponent and the logarithm of that number. I'm trying to think, what do people try to do to this that's weird? I can't think. This one people are usually pretty good at. They don't do weird things. But I guess we'll see what kind of weird things people try to do. All right, so we're going to use properties of logs to expand the logarithmic expression as much as possible. Where possible, evaluate the expressions without using a calculator. Now, in some cases, we're not going to be able to do that. We're just going to have to leave the log in our answer. Sometimes we'll have more than one term, and we can simplify part of it, but not the other part. That's okay. Whatever we can simplify, we'll simplify. All right, so log base 6 of 7 times 3. This is going to use the product rule. So don't just say log base 6 of 21, done, because you haven't actually used a rule at that point to rewrite the expression. We're trying to expand it. If you multiply 7 times 3, you're not expanding the expression. If anything, you're condensing it further. When we expand it, we want to kind of make it longer, make it go out more. And you might be thinking, why would we do that? Don't we always try to simplify things and condense them down? Not always. You'll find that when we're working with equations, you're going to sometimes have to expand the expressions. So we're going to practice that now. So we're going to use the product rule, and we're going to take log base 6 of 7 and add it to log base 6 of 3. And that's how we're going to expand this expression. Now, if you can simplify either of these terms without using a calculator, then do so. But if you can't, then let it be. Don't try to get a decimal equivalent. Leave it exact if you can't simplify it down to some sort of integer or fraction. This is the expanded expression. It's done. There's nothing else you can do to this. Number 2 is log of 100x, and we're going to expand this out. And this one we'll be able to simplify a little bit more. This is one of those steps where, like, it's optional. I could see where you would have seen the multiplication without writing it, but I think it's helpful just to write it so that it matches up with our rule a little bit more clearly. We're taking the log of 100 times x. So we'll go ahead and use that product rule to split this product into a sum of 2 logs. So the log of 100 plus the log of x. Now don't put a box around it. The log of 100 we can evaluate without using our calculator. And if you're like, how would I do that? Well, if you feel more comfortable writing this with a base of 10, do that. You don't have to do that. It's an option. It's an implied base of 10. To evaluate this logarithm, you're asking yourself, 10 to what power gives me 100? And the power would be 2. So we're taking 10 squared to get to 100. So it must be that the log expression is 2. Now the second term is just log x. You can't simplify that. It's done. So this is an example of, we can simplify one term a little bit, the other term we can't simplify, and that's okay. Simplify what you can. Don't leave your answer as log 100 plus log x. My math lab will tell you that your answer is equivalent to the correct answer, but it's not written in the proper form. Check your directions, and your directions are going to say to simplify your answer. Simplify your answer includes evaluating logarithms. Questions on using the product rule? Okay. Now we have the quotient rule. This time, I'm going to take log base b of m over n and split it up into log base b of m minus log base b of n. So we have log base 10. We can write it or not write it. Doesn't matter to me. Log of x minus log 10. Now you also had in your logarithmic properties log 10. Log 10 is 1. The base is 10. 10 to the 10 is, or I'm sorry, 10 to the first power is 10, but in that case, the 10s would match. Log 10 is 1, so we can just write this as log x minus 1. Side note, log 10 equals 1 because log base 10 of 10 equals 1. Because 10 to the first equals 10. I don't know. I always try to include a little bit more information in case you were really confused and you watch the video later and you're like, why didn't she go into more detail? Try to go into more detail. We're going to do the same thing for number 4. This time we have a natural log. So we're going to write this logarithm again using the quotient property. So we'll take the natural log of e squared minus the natural log of 9. If you would like to write a script L so it doesn't look like a 1n, that's fine. I usually write a script L, but for some reason I didn't here. Well, not equals, minus. Sorry. And then we'll simplify. Now, the natural log of 9, we cannot simplify without using a calculator. E to some power gives us 9. I don't know what the power is. Doesn't matter. Leave it exact. As far as this expression, we can simplify this a little bit further. Now, if you would like to use the property that we talked about before, like the base would be E, the bases match, use the exponent, that's fine. Or you could even use our power property. The power rule says that log base b of m to the p is equal to p log base b of m. So if you prefer to use the power rule, you can also do that here. So we did evaluate this log like 10 minutes ago when we were in the last section, but we could use that power rule here. Now I'll use my script else because I have to get back into that habit. Oh, sorry, I pulled the 2 down. So the power rule says that we can take the power out of the exponent and move it in front of the logarithm as a constant multiple. And then let's say you didn't remember log of e squared, but you did remember the log of e. Perfect. You can evaluate this without using a calculator. If you still are like, I don't remember what it is, that's fine. The bases match, so you just use the exponent, which is 1. So you have 2 minus the natural log of 9. Everybody has a different way in which they look at these logarithms when they're evaluating them. If you remembered from the last section that the natural log of e squared was 2, that's fine. You don't even have to write out all this work. Questions on numbers 3 or 4? Okay. All right, using more of this power rule here, log base n of x to the 5th power. So you're going to take your exponent out of the exponent and move it in front of your logarithm. So this exponent 5 is going to become a constant multiple in front of the log. Then you have log base n of x. Now, some people question whether or not this is actually expanded, and sometimes I guess it's not clear, because if you're being asked to expand this expression, you're maybe thinking like, these two look equally expanded. I don't know which one's which. Anytime you're being asked to expand, you always want to take the log of a product and split it up into the sum of 2 logs, or you want to move that value out of the exponent and put it in front of the logarithm. That is considered expanded. So your expanded expression should not have any exponents on the log expression. That's just something you'll have to get used to working with as you expand. And then, same idea here. This time, though, I did not give you an exponent. I gave you a radical expression. So we're going to rewrite the radical expression using a rational exponent. So this will be the natural log of x to the 1/7 power. It's kind of necessary to rewrite the logarithm with a rational exponent before you apply your power rule. And then you're going to move that exponent in front of your logarithm. And that's how you do that. We're going to combine some of these rules in the next step. Before we do that, does anybody have a question here? Okay. Wonderful. Okay, so now we're going to use our log properties to expand the expressions. Where possible, we're going to evaluate the log without using a calculator. So same directions. This time the expressions are just going to have a little bit more going on with them. Now, it's important to note which rule you're going to apply first. It's also important to note what is actually being done to your function. Whatever you do, do not use the power rule here first, because the 4 is not being applied to yz. The 4 is only being applied to z. So if you take the 4 out of the exponent and move it in front of the log, you are saying that the 4 is applied to both y and z, which it's not. So I want to make sure I note that, because this is a very common error that people would say this. And we will go over some examples where we do have parentheses. This expression would look like that. So I want to make sure that we understand the difference. So in this case, the 4 is being applied to the product yz. In this case, the first case you were given, the exponent is only being applied to the z. Okay, so now that we know what it isn't, let's discuss what we should do. In order to get this 4 out of the exponent, you're going to first have to split up this product so that you have a sum of 2 logarithms, and then you can work on taking that exponent out. So we're going to rewrite this as log base b of y, and then it's addition because we're looking at a product, log base b of z to the 4th. And now to finish this one, you just have one thing left to do. The log base b of y is already simplified. Just rewrite the second expression by moving that 4 out of the exponent, and it becomes 4 log base b of z. And that's it. You cannot simplify log base b of y, and you can't simplify log base b of z. So we'll leave it. Question on number 7. Okay. Number 8. Log base 6 of x minus 6 divided by x to the 8th power. Now this one, I don't think you would try to pull that 8 out in front yet, because it's a little bit more obvious here that the 8 is just on the x. It doesn't apply to the whole expression. So we're going to split this up using subtraction. So we're going to use that quotient rule. And remember, I can't work on the 8 yet because it's only being applied to the denominator of your quotient. So we have log base 6 of the numerator, x minus 6. And then remember, when it's division, we subtract. Log base 6 of x to the 8th. Now, some of you are a little bit faster than others, and some of you are automatically going to write minus 8 times log base 6 of x. That's fine. It's not a huge leap to get from one step to the next. So if you were to skip that step and go straight to this one, that would make sense to me. And then that one is done. Whatever you do, don't say that this is log base 6 of x minus log base 6 of 6, and then say, oh, this must be log base 6 of x minus 1. Don't do that. Okay? You cannot take the log of a difference and turn it into the difference of two logarithms. We don't have a property for that. I know it seems like something you really want to do. You want to distribute that logarithm, but you cannot. You cannot distribute the logarithm. This is your answer. So I will write this note. You cannot distribute logarithms. All right, now we're going to condense some logarithmic expressions. Before I do that, does anyone have a question about my note? Now, same rules here. This time we're just going to go the opposite direction. So we're going to take the sum of two logs and turn it into the log of a product. We're going to take the difference of two logs and turn it into the log of a quotient. And then we'll take p times log base b of m and rewrite it as log base p of m to the log base b of m to the p. I feel like this p looks more like an exponent here. On the last page, it looked less like an exponent to me. But that is what we're going to do now. We're going to work in the opposite direction. So when we're condensing, we want the powers in the exponent, not out front. And then we want to take any sums and turn them into products and differences and turn them into quotients. So we're going to use the property of logarithms to condense, write the expression as a single logarithm. So we don't want a bunch of terms here. We want a single logarithm whose coefficient is 1. We'll evaluate the expression if we can. So in this case, we have log base c of m plus log base c of n. Be extra careful here because it must be the case that your bases match. We didn't have to worry about that so much when we were expanding, but when we're condensing, make sure you're not condensing where you cannot condense. It must be the case that both of these expressions have the same base. So we're going to rewrite this as log base c, and instead of taking a sum of two logs, we're going to write the log of a product. Log base c of m times n. I would include parentheses around this. They're probably not essential, but when in doubt, include parentheses. Questions on 9? All right, number 10. Okay, so you have two different things going on here. First of all, you see that you have a coefficient of 3 on your first logarithm. However, you don't have 3 times these two logarithms. It's only 3 times the first logarithm. So in order to combine these together, you need to move that 3 back into the exponent before you can go any further. So you have log base x of 2 cubed plus log base x of 3. And then we'll keep simplifying. Log base x of 2 cubed, which is 8, plus log base x of 3. Now, both of these logarithmic expressions have the same base. Their base is x. Because they have the same base, we can go ahead and combine them. So we're going to take the sum of the logarithms and turn it into the logarithm of a product. So the log base x of 8 times 3. And if you feel like you get really good at this and you can skip this step and move straight to log base x of 24, that's fine. What I don't want you doing is going from here to there. I need to see a little bit of work in between. Now, the parentheses on this one are not essential because you just have this one number in the argument of your log. It's when you have multiple variables and different things going on in your expression that the parentheses become more important. Okay. I want to talk about the change of base property, and then whatever time we have left after that, I want to just go over a couple more of these expanding and condensing problems, because some of them can get a little bit more hairy than this, and I want to make sure that we cover some that are a little more involved. But the change of base property is also life-changing for you, because it's going to help you to figure out how to evaluate logarithms on your calculator when your base is something other than e or 10. So we're going to talk about the change of base property. For any logarithmic bases a and b, and any positive number m, log base b of m equals log base a of m over log base a of b. The logarithm of m with base b is equal to the logarithm of m with any base divided by the logarithm of b with that new base, yada, yada. Doesn't matter. What this means is that you can take log base b of m and rewrite it as the log of any base of m divided by the log of that same base of b. A lot of times we're going to use natural logs for this. So we can say that log base b of m, lost my focus here. Sometimes when I do this, it comes back, but other times not so much. If I threaten to do this manually, it always fixes itself. Okay. A lot of times we're going to write this as just natural log m divided by natural log of b. Depending on what we're actually working with, we might write this as a base 10 log. Doesn't matter. You can write this as log base 5 of m divided by log base 5 of b. I don't know why you would do that, but you technically could. The moral of the story here is that to evaluate log base b of m, you can rewrite this as a quotient using a natural log or a log, which most of the time is what you're going to be using. Natural log probably being the easiest one, but it depends. But you're always using the m in the numerator and then the base in the denominator. And you can make the base of your new logarithms any base you want as long as they match. So I will show you how to do this. And we'll use our calculators here. If you would like to use your calculator to evaluate log base 5 of 8, I do think there's a function in your calculator for it. I couldn't find it at a quick glance, but I'm going to be asking you to use the change of base rule anyway on your test. So I don't really want you to just be using some function in your calculator, because that would defeat the purpose. And you would not be following instructions. You can write this as log of 8 divided by log of 5. I want to show you that you'll get the same answer regardless. So maybe we'll do this 2 different ways, and you can see that the quotient will come out the same. You could also use a natural log. Those are the ones that we can use in your calculator. Just make sure the 8 is in the numerator, and then that base with the 5 is in the denominator. We can kind of see this. Okay, so log of 8, don't forget to close your parentheses. That's very important. Divided by the log of 5. And don't switch between log and natural log. You got to keep the same base on each one. So log base 10 has to go with the log base 10. And you get approximately 1.292. If you did the same thing with natural logs, you also get 1.292. As long as you choose the same base for the numerator and denominator, does not matter. You can evaluate these logarithmic expressions using the change of base formula. Don't you feel like this is life-changing? So many things you couldn't do like 2 hours ago that now you're like, oh my gosh, I can finally do this in my calculator. This is amazing. So many wonderful things we learn in math. Every class. Yeah, that's every class. Well, that's great that we feel like we're learning so much in every class. I agree. Okay. But sometimes you head into a class and you have no idea what you don't know. Whereas before you were like, I have no idea how to enter this logarithm in my calculator. Okay. Log base pi of 15. Again, you pick. You can do a base 10 or you can do a natural log. But just whatever you do, make sure the 15 is in the numerator and the pi is in the denominator. You could also write it with a natural log, you decide. But now you know how to use both. Just don't forget to close off your parentheses. Oh, if you're not sure how to pull up pi, it's second and then your caret. I'll pull up pi. Don't put in 3.14. Pull up the actual pi. It's going to have all the digits in there. So second, caret will get you to pi. And you get approximately 2.366. All right, now where is my book? I was going to see if there was a good like expand condense problem we could do. Oh, and by the way, this is it for 4.3. Well, we'll do 4.4 Wednesday. So if you want a bit of a crazier expand condense, I was going to find a good one. There's nothing like too nuts in here. Ooh, how about we condense 1/4 log base b of x minus 2 log base b of 5 minus 10 log base b of y. That's a good one to condense. So remember, if we're condensing, we want to have those powers back in the exponents, not as constant multiples. So start out by putting those powers back into the exponents. Now, when we're expanding, we take a radical and we rewrite it with a rational exponent. But when we're condensing, we normally will take that rational exponent and turn the expression back into a radical expression. So let's go ahead and do that. And instead of writing x to the 1/4, we'll write the 4th root of x. 5 squared is 25. And then y to the 10th, we really can't simplify any further. Now, this one's a little more confusing because it has 3 terms in it. When you're subtracting, work with the first 2 terms and then work your way from left to right. So let's go ahead and combine these two using your quotient rule. We have the same base and we're subtracting. So we're going to rewrite this as a quotient. This is log base b of the 4th root of x divided by 25, and then minus log base b of y to the 10th. Now, use your quotient rule one more time. You're subtracting. This time we're going to go ahead and take our log base b We're gonna write this now as a quotient, but if you find this looks a little bit crazy, let's see, you have your original, and then you're dividing it by y to the 10th. We can look at how you would show that division. If you feel comfortable without doing these extra steps, that's fine. I feel like with complex fractions, sometimes students get really stuck. So side work, the 4th root of x divided by 25 divided by y to the 10th is equal to the 4th root of x divided by 25. And remember, if you're dividing two fractions, you're multiplying by the reciprocal. So if you want to think about y to the 10th as y to the 10th over 1, probably find that helpful. So instead of dividing by y to the 10th, multiply by its reciprocal, 1 over y to the 10th. And then go back. We can, sorry, I meant to simplify this one step further, but you can probably see that multiplication. So we really have log base b of the 4th root of x divided by 25 y to the 10th. And I don't think you're going to get anything much crazier than that. Let's see what else is, if I can find anything super interesting. Not really. We do have like 2 minutes. Maybe we should do another expand. Gotta capitalize on all this extra time. I don't know if you have a back to your page, but I'm just going to do this one on the back, and I'll keep it up for a minute in case you want to copy it down elsewhere. How about expand log base 5 of the square root of x divided by 25y cubed? Okay, now notice that you have a product in your denominator. You can't touch it until you split up your fraction. So you want to get rid of this quotient first. Rewrite this as log base 5 of the square root of x. And if you want to automatically go from the square root of x to x to the 1/2, you'll be saving yourself a little bit of time. So we'll take log base 5 of x to the 1/2 minus log base 5 of 25y cubed. When in doubt, include your parentheses just so that nothing is left to question. Now, there are a couple of things we can do. One thing is we can go ahead and move this exponent in front of our logarithm in the first term. That term is done. And in the second term, we still have this product. Now, we also have a cube on our y, but remember the 3 is not being applied to both of these factors. It's only being applied to y. So we're going to split this up as a sum before we do anything else. However, you have subtraction here. You must include parentheses. Otherwise, that negative sign is not going to get distributed to both terms. The parentheses are key. And you are almost done. Log base 5 of 25, well, 5 squared gets you to 25, so that's 2. Then you have minus, because we're going to distribute that negative sign. I'm going to pull the exponent down. I'm going to say this is 3 log base 5 of y. And that is your expanded expression. If you want to do a couple more of these, stick around for the office hour. Otherwise, I'm a minute over. I'll put up some homework for you. And I will see you Wednesday for 4.4 solving equations. Have a wonderful evening. Bye.